All right. So again, welcome to this new edition of Ordinary Differential Equations, AMAT 311. My name is Marius Beceanu, Mariusbeceanu. This is a Romanian name, so I am Romanian. Um, I think, okay, let's start with this practical information that's written on this page. Um, All of it is also included in the course syllabus, which is on the course Blackboard website. And I'm also going to um, put more information on the course Blackboard website. So I'm going to populate all that information into the web pages that are on the Blackboard website. So my office is Earth Science 136B. That's pretty close to here. But I don't think this term we're going to do a lot of in-person meetings just because of the conditions. The office hours will be online. Each office hour will be a Zoom meeting, which I'm going to announce maybe 5 minutes before the start of the office hour. So probably there will be one tonight from 6 to 7, and in general on Mondays from 6 to 7, and on Thursdays and Fridays from 3 to 4 in the afternoon. The best and easiest way to reach me is by email. I usually respond to emails in maybe 2 to 3 hours. Sometimes I respond much faster. Very early, I respond more slowly. Let's see. No more resonance. Oh, okay. Little bit of resonance. So we can also schedule more office hours by appointment if you cannot make it to these 3 office hours that are announced up there. So also by email, please email me if you want to schedule other office hours. The textbook for this class, let me show you. This is the textbook. It's more of a reference than a full textbook. So it includes the formulas, the main formulas that appear in this course. It does not include proofs, and it includes a lot of exercises which are similar to the exercises we will be solving in the course. So for each chapter, they have maybe something like 20 solved exercises and 20 unsolved exercises. The main way that I will use it is by assigning problems for review for the midterms and for the final exam from the textbook. And at the same time, of course, it can also serve as a reference. Like I said, it contains a list of formulas for each topic and several solved problems if you want to see how to solve each specific type of problem that they have in the textbook and which are very similar to the types of problems we will be solving in the course. I think I also have 2 or 3 topics in the course which are not covered in the textbook. For those, the main reference will be the homework. And of course, the lecture notes for and the course itself. So we'll see when we get there. Grading, as you see, will be based 50% on the homework. There will be around 12 or 13 homework assignments for the course. So roughly one every week. But some of them will be longer and harder. Some of them will be shorter. In general, each of them has around between 5 and 10 problems. So let's say roughly 7 problems. The homework will be on a website. I have set up the website last night, but I haven't posted homework yet. You can try and see if you can log on to the website, but there is no homework there yet. So you can just try your username and password. Your password is your first name as it appears in the course records. So please let me know if you have any problems getting in. This is all that you can do right now. I mean, try to log on. There is no homework. But hopefully I'll post some homework tonight, hopefully. The midterm dates are roughly one per month. So there will be one at the end of this month and one at the end of next month. And the final exam will be, is officially scheduled on the 12th of May. For all of these, I think the way we'll do it is that I'm going to specify actually not only one day, but maybe 2 or 3 days. And over those days, you can pick a time when you would like to take it. And I'm going to email you the exam at that time. And then you'll have 2 or 3 hours, probably 2 hours for the midterms and 3 hours for the final exam to solve them and scan it and or maybe take a picture and send me back by email your exam. So, any question up to here? Yes. Okay, but if I turn the microphone louder, maybe there is too much resonance, but let's try. Is this better? But did you get this information that I just said? All right, so let's see, what other topics? So in this course, I'm going to present an overview of all the topics in this term, very briefly. And then I'm going to give a couple of examples for how to solve some ordinary differential equations. And then next time we'll continue with the actual definition of an ordinary differential equation and more like that. So the first topic in the course will be an introduction, the definition of an ordinary differential equation, the classification of ordinary differential equations, and there are 3 main criteria used in practice, namely ordinary differential equations are classified into linear equations versus nonlinear equations. They are classified by order. So first order equations, second order equations, third order equations, and so on. So an equation can have an arbitrarily high order, which is an integer. And another criterion that will come up in a more limited way, maybe for one topic in this course, is autonomous versus non-autonomous equations. We'll also define ordinary differential equations. We'll see what is the standard form of an ordinary differential equation, how to write it in standard form, what is and what is not an ordinary differential equation, and another classification, but not for equations, but for problems based on ordinary differential equations, is into initial value problems versus boundary value problems. So when we solve an ordinary differential equation, we specify the equation together with often some conditions that can be used to solve it. And these can be initial conditions or boundary conditions. So then the equation together with these conditions forms either an initial value problem or a boundary value problem. So these are the two main types of problems. And if we don't specify either initial conditions or boundary conditions, then the equation usually admits an infinity of solutions, and that's called the general solution of the equation, and we'll also do that. So after this theoretical introduction, we are going to look at some solvable types of first-order differential equations. So in practice, these solvable types of differential equations appear much more often than maybe should be the case. So maybe 90% of the equations that arise in science, in engineering, belong to one of these types. This is maybe a coincidence, but so maybe 90% of these equations belong to types that we know how to solve. On the other hand, not every type of ordinary differential equation can be solved explicitly by an explicit formula. So this is just our luck that 90% of them in practice can be solved. So these types of equations are called solvable by quadratures. And we're going to study 5 of these types. In general, there exist maybe many more less known types. There are maybe 10 very well-known types and maybe 10 or 20 more less known types of equations for which we have an algorithm that can be used to solve them. So after we identify the equation type, if we know it is of that type, then there exists a method that we can use to solve all the equations of that type. So as I said, there are maybe 10 well-known types, or around 10, out of which we are going to study 5 of these first-order types of differential equations. And then towards the end of the course, we are going to study more methods to solve linear equations. So for linear equations with constant coefficients, there are several ways of solving them. And I'll say more in a couple of minutes. So again, if an equation is sufficiently complicated, or if it just doesn't fit into one of these types, so if you take a random equation that you can write, then chances are that it is not solvable using one of these methods. So here is an example. I tried to give one of the simplest possible examples. For example, the equation y prime is equal to e to the y plus y sine x is not solvable by quadratures. So there is no algorithm such that you plug in the equation and you get the solution as an explicit function. So the solution is not going to be something like, I don't know, 5 cosine of x squared plus 3x. You're not going to be able to find an explicit solution like this. So in addition to these 3 types that we are going to study, there are at least 3 more that we are not going to study: Riccati, Clairaut, and Lagrange. Let me see, I think on the main page I say more. Okay, so these are the types that we will study. Like I said, there are 5 of them, and they are covered in the textbook. We have separable equations. That's the type we're going to start with. And maybe this is the most useful type, because maybe 40 or 50% of equations that you are likely to encounter in practice belong to this type. So it is one of the simplest types, and it is one of the most widespread types. Okay. And again, this is probably just a fortuitous coincidence, but it's a good thing that even though in theory we cannot solve, so there is no general method for solving ordinary differential equations, in practice, there is a method that works for so many of them. So then we are going to look at linear first order equations and then at exact equations. And based on these 3 main types, there are 2 other types which are solvable by substitutions. This means we can use a substitution to reduce these 2 other types to one of the 3 types above. So homogeneous type equations can be reduced to separable equations, and Bernoulli equations can be reduced to linear first order equations. So these are a little bit more complicated because solving them takes twice as much time. So first you have to use a substitution to reduce them to one of the previous types, and then you still end up with a new equation to solve, and you still have to solve it. So in addition to this, as I said, there are some other types: linear equations with constant coefficients, Cauchy-Euler equations, and systems of linear equations with constant coefficients, which we are going to study towards the end of the term, maybe in the last third or the last half of the term. So any question up to here? All right, so then next, after we study first order ordinary differential equations, we're going to look at some applications of them. So we're going to look at scientific models based on first order ordinary differential equations. And then later in the course, we're going to look at models based on second order ordinary differential equations. So models based on first order equations are exponential growth, exponential decay, Newton's law of heating and cooling, the logistic growth model, solution mixtures, and then falling with air resistance is actually based on a second order equation, but it can be reduced to a first order equation. And then later in the term, probably after we study the Laplace transform, we're going to look at spring mass systems and RLC circuits. So those are second order models. The last 2 are second order models. And by looking at these models, first of all, these are some of the most widespread and simplest models that can be solved using ordinary differential equations. And then maybe we're also going to get some understanding of how various scientific and engineering phenomena are modeled using ordinary differential equations. So in practice, many scientific phenomena can be modeled using systems of ordinary differential equations. So any phenomenon that is described by some finite number of quantities, like let's say you have a recipient that's filled with gas, and if if that gas can be described by a finite number of quantities like its temperature, its pressure. Here we have two quantities, and these quantities depend on time, then usually the way in which they depend on time is described by ordinary differential equations. And then we can model this using a system of ordinary differential equations. If you want to model a more complex phenomenon, so for example, if you have this recipient filled with gas and you want to take into account not just the temperature and the pressure of the gas in the whole recipient, but maybe you want to take into account the temperature and the pressure at each point inside the recipient, then you're going to have to use partial differential equations. So in general, more complicated models are described by partial differential equations. But ordinary differential equations are enough to describe a very wide range of phenomena, and the models are usually good enough to use in practice. So after we studied these explicitly solvable types of ordinary differential equations, we're going to take a break and look at those equations that cannot be solved explicitly. So there exist methods for obtaining the solutions in these cases, but the solutions that one obtains are not given by an explicit formula. So what kind of solutions can we get? First of all, we are going to look at the theory of existence and uniqueness of solutions. This is going to be one course, one lecture. So even in cases where we cannot solve the equations explicitly, the most basic thing we are interested in, the most fundamental thing we are interested in is knowing whether there exist solutions or not. And if the solutions exist, whether they are unique. So even if we cannot find a solution, we are still interested in knowing whether a solution exists. And this is the main theorem in our course. It's called the existence and uniqueness theorem, or sometimes Picard's theorem. And then there exists a variant of this, which under weaker conditions guarantees only existence and not uniqueness. And that's called Peano's theorem. On the other hand, this Picard's theorem the existence and uniqueness theorem is based on an explicit method of constructing solutions. So again, it's not going to give us an explicit formula for the solutions, but what it's based on is the existence of a sequence of approximations to the solution. So the proof of this theorem gives us this sequence of approximations to the solution. So even if we cannot find a solution explicitly, we can find some very good approximation to the solution. So this is one way in which we can solve equations when we cannot find an explicit formula for solving the equation. So one thing that we can do instead is find a very good approximation for the solution. Yeah. So this is what we are going to briefly talk about when we talk about the existence and uniqueness of solutions. Okay, another approach that we can use when we cannot find a solution explicitly, or sometimes even when we can find an explicit formula for the solution, but the formula is maybe too complicated to be of actual interest, or maybe we just want more understanding of this complicated formula. So one other method is the geometric approach. So in this topic, we're going to focus on qualitative properties of the solution. So for example, is the solution periodic? This means after a time has elapsed, does the solution go back to the initial state? So we start with some initial condition for the solution. Does it, after a time has passed, go back to that state? Or is the solution constant? So this is called an equilibrium. If we start with certain initial conditions, will the solution stay at those values for all time? Or does it approach an equilibrium? So maybe we start with some initial conditions, and over time it approaches some constant value, so, which is called an equilibrium. Or does it approach a periodic solution? Maybe it's equal to, so maybe we start with some value, and then after a while it approaches, as I'm saying, a periodic solution. And then is the equilibrium stable or unstable? So many of these questions make more sense for 2 dimensions and higher systems of ordinary differential equations. What we are going to be looking at in this course is a simpler case, the 1-dimensional case. So the case where we have just one equation, just one ordinary differential equation. In this case, the analysis is relatively straightforward. There is this method called the phase line method. And this is what we shall study in this course. So this is not in the textbook, but it's again, it's relatively straightforward. We'll see when we get there. Then, in the last third of the course, we're going to look at, it looks like I skipped a topic here. Okay, so actually before going into and looking at linear equations here, we're going to look at series solutions. So this is another way of computing the solution of an equation when we cannot get an explicit formula for the solution. So series solutions, so power series and generalized power series solutions mean that we solve the equation by a power series. So we don't get an explicit formula like sine of x or x squared plus 7 for the solution, but instead of that, we get a power series. So maybe 1 plus 2x plus 7x squared plus 3x cubed plus etc. So the solution is going to be given as the sum of an infinite power series whose coefficients we can compute. So again, obtaining the solution as the sum of a power series in general is not as satisfactory as being able to get a closed form answer. So being able to get an explicit formula for the solution, but it is more general. And then sometimes, but usually not, we can identify the power series and we can recognize that it is a well-known function. But in general, the solution is just given by that power series. So we're going to look at power series and generalized power series. And as I say here, there is at least one more type of series that are used in the study of differential equations, namely Fourier series, but those are used in the study of partial differential equations, so not in our course. And then after that, we're going to talk about linear equations. So linear equations have several properties that make them easier to solve than general ordinary differential equations. So it turns out that for linear equations, for linear ordinary differential equations with constant coefficients, we can solve them for any order, and there are several methods used for solving them. One method is this method of the auxiliary polynomial and the method of the undetermined coefficients. Another is the method of variation of coefficients. We may skip over this topic. We'll see, depending on how much time we have. And another topic is the Laplace transform. This is very widely used, especially in engineering, but also in mathematics. So this method leads to an interpretation of solutions of linear ordinary differential equations in terms of exponential growth, exponential decay, and oscillation. So by using the Laplace transform, it is relatively straightforward to tell whether the solution of the equation has exponential growth, exponential decay, or oscillation, or some combination of these. And these are the three main possible behaviors of solutions to linear ordinary differential equations with constant coefficients. And then, finally, we're going to look at the matrix exponential. So the matrix exponential is a method for solving systems of ordinary differential equations with constant coefficients. So the nice idea is that just as real numbers and complex numbers have an exponential, so just like you can compute the exponential of the number 7 or the exponential of 0, by the way, how much is the exponential of 0? How much is e to the 0? 1. So in the same way, we can compute the exponential of matrices. So but they have to be square matrices. So, and that's useful in solving systems of ordinary differential equations with constant coefficients. And finally, this is a very important method in practice because it is used in general by computers, namely numerical methods. So numerical methods are what we can use when everything else fails, or when we don't want to spend time computing the power series of the solution. Or again, when we plug an equation into the computer, then this is the first thing it is going to try in order to solve it in general. So numerical methods give an approximation to the solution, usually based on a grid of points. So we take the interval over which we want to solve the solution, and then we pick some points in that interval, maybe 1,000 points, maybe 1,000,000 points, and we approximately find the value of the solution at each point based on the values at the previous points. So we discretize the problem. Instead of solving it over the whole interval, let's say we start with the initial condition at time 1, and then we solve the equation approximately finding the value at time 1.01, then 1.02, 1.03, etc. So this is how often computers do. And then, of course, after we find these values at a discrete set of times, then we can interpolate between them. So if we know the value at time 1 and the value at time 1.01, then we can guess what the value has to be at any time in between. But again, this is only an approximation, and it has an error. And these numerical methods are based on controlling the size of the error. So by doing sufficiently many computations, we can say with certainty that the error is going to be no bigger than 1/1,000,000 or 1/1,000,000,000, or however big is an acceptable error for us. So again, this is what computers do, and you can even specify the size of the error. And the most basic, and probably the only one that we are going to study, is Euler's method. So again, this is the most basic, the most fundamental one. This is also the prototype for all the others. The other ones are more complicated, but they're roughly based on the same idea. So then we're going to maybe look at Hume's method, the midpoint method, and Runge-Kutta methods, but probably no homework about the Runge-Kutta methods. So, any question up to here? So if we have more time at the end of the course, then probably we'll spend some time on review, or maybe I'll introduce one more extra topic, but again, without any homework and maybe without requiring it for the final exam. But that's only if we have extra time at the end of the course. So any question up to here? Or comments up to here? Okay. So what is an ordinary differential equation? So first of all, what is a differential equation? A differential equation means an equation that contains derivatives. So an equation that contains the derivatives of the unknown functions, and there can be one unknown function or there can be several unknown functions when it's part of a system, is called a differential equation. And there are many other types of equations that you have encountered so far. So for example, quadratic equations are algebraic equations. For example, the equation x squared plus 2x plus 7 is a quadratic equation, and it's an algebraic equation. Differential equations are a type of functional equations. This means, so what are functional equations? They are equations whose unknown is a function. So for example, one of the simplest ordinary differential equations is the equation y prime is equal to y. So the derivative of the function y is equal to the function y. So the unknown is the function y. So let's say y is a function of the variable x. The unknown in the equation is the function y. So when solving an ordinary differential equation, our goal is to find a function. Okay. So there are two types of differential equations. There are ordinary differential equations and partial differential equations. In our course, of course, we are going to study ordinary differential equations. So ordinary differential equations mean that the derivatives are with respect to a single variable. In practice, the single variable is often the time, t. But sometimes you're going to denote it by t, sometimes you're going to denote it by x. What matters is that it's just one variable. If the equation involves partial derivatives, then it is called a partial differential equation. So they are not going to be covered in this course. So here are some examples of ordinary differential equations. Let's say x prime is equal to x. This means x is the unknown function. Probably it's a function of t, but it's not specified in the equation. And we are saying that the derivative of x is equal to x itself with respect to t. So the derivative of x with respect to t is equal to x itself. Here is an ordinary differential equation that involves two functions. So here it says x prime squared plus y prime squared is equal to 1. So this equation probably cannot be solved by itself. It makes more sense as part of a system of equations. Or here's another example. Y double prime minus 3y prime plus 2y is equal to e to the x. So this has the second derivative of y minus 3 times the first derivative of y plus 2 times the function y itself is equal to e to the x. So in general, any letter can be used to denote the unknown function, and any letter can be used to denote the variable. So here, y is the unknown function, and x is the variable. So y is a function of x. And you have to read this from the equation, or sometimes it is given to you. Let's say y is a function of x. So usually the variable is denoted by x or t, and the unknown function is denoted by x, y, or z. But this is not a rule, so again, any letter can be used to denote the unknown function, and any letter can be used to denote the variable. So the unknown functions are also called dependent variables, and the variables, so like e to the x here is a variable, are also called independent variables. So, okay, so here are some more examples of partial differential equations, Diophantine equation, integral differential equations, and functional equations. So in addition to equations that involve derivatives like differential equations, one can have equations that involve integrals, which are called integral equations. Or one can have equations that involve a combination of integrals and derivatives, which are called integral differential equations. The reason why these are not as widely studied as differential equations is that usually by taking derivatives in the equation, we can reduce integral equations and integral differential equations to differential equations. So they're not as much the subject of study, of separate study, as differential equations. And for example, we are not going to spend more than a couple of words on them in this course. So here is the usual notation for derivatives. So how do we denote derivatives when they appear in our ordinary differential equations? So all the derivatives will be ordinary derivatives, again, not partial derivatives. The most widespread notation is the prime notation. So x prime, x double prime, x triple prime. And this is a notation for the fourth order derivative. So people use Roman numerals in this manner. So x to the power iv means the fourth derivative of y. And then x to the power v would mean the fifth derivative of y. But then usually after the third derivative, instead of using Roman numerals, one uses Arabic numerals in parentheses. So x to the power 4 between parentheses means the fourth derivative. X to the power 5th between parentheses means the fifth derivative of x, etc. So x to the power n between parentheses means the nth derivative of x. So another widespread notation for derivatives is the Leibniz notation. This notation has the advantage that it always tells you what is the variable with respect to which we are taking the derivative. So for example, here I'm writing dx over dt. This means x is a function of t, and I'm taking the derivative of x with respect to t. Or here, d squared y over dx squared means y is a function of x, and we take its derivative with respect to x, etc. And another widespread notation is Newton's dot notation. So this is always used to denote derivatives with respect to time t. So x dot, x double dot, x triple dot, even these mean the derivative of the function x with respect to the variable t, which denotes time. And I'm not going to use it as often in this course, but I think, for example, in the textbook, they used it in a couple of problems and exercises just to familiarize you with this notation. So there is another widespread notation for writing ordinary differential equations, which is the differential notation. And there are a couple of specific types which are very often used, which are very often written using that notation. And we're going to talk about the differential notation more when we get to those types. So two of the types that we study, namely homogeneous type equations and exact type equations, are often written using differential notation. So then when we study those types, we have to talk about differential notation because traditionally they are written using differential notation. So finally, I think we have just enough time to very briefly talk about a couple of examples. So here are some very simple examples of ordinary differential equations. So this one is very simple. Maybe the one on the next page or next page is going to be less simple, but they are straightforward to solve. So there is nothing that can be simpler than this. So this is, again, one of the simplest possible ordinary differential equations. So here we have x is a function of t. So x is a function of t. And we want to solve the equation. The derivative of x with respect to t is equal to sine of t. So how do we solve it? We solve it by integrating both sides. So this is often what we have to do when solving ordinary differential equations explicitly. So this is what we'll be doing in the first third of the term. We integrate both sides of the equation. However, usually it's not as straightforward as this. Usually we first have to do some algebraic manipulations until we get to the point where we can do this. So this is just exceptionally simple because we don't have to do anything except integrate both sides. So if the derivative of x is equal to sine t, then we can integrate both the left-hand side and the right-hand side, and they should still be equal. So the integral of the derivative of x is x itself, and the integral of sine of t is the integral of sine of t here, which is minus cosine of t plus a constant. So in other words, if the derivative of x is sine of t, then x is an antiderivative of sine of t. And the antiderivative is not unique, as I say here. So the antiderivative of sine of t is minus cosine of t plus a constant. If we are not given initial conditions for this equation, then this is the solution that we get. So as promised, we actually get an infinity of solutions. So minus cosine t is a valid solution. Minus cosine t plus 100 is a valid solution. Minus cosine t minus pi is a valid solution. Minus cosine t minus tri square root of 2 is a valid solution. So the equation has an infinity of valid solutions, and they are all antiderivatives of sine of t. And we have solved the equation. So again, this is one of the simplest possible equations. All that it takes to solve it is we integrate both sides. So the antiderivative of the derivative is the function itself, plus a constant maybe. And the antiderivative of sine of t is minus cosine of t plus another constant. And okay, so now let's look at this with an initial condition. So this is how this equation was like with an initial condition. So again, the pairing between the equation and an initial condition is called an initial value problem. So this is an initial value problem. It consists of an equation and an initial condition. So how do we solve this? One straightforward way of doing it is we use the solution that we already found on the previous page. So on the previous page, we found that the solution in general is of the form minus cosine t plus a constant. But now, because we have an initial condition, we can determine the constant. So we look at this general form of the solution here, and we plug in. So what does the condition say? It says that x is 1, so we plug in 1 for x, at the point where t is equal to pi over 2. So we plug in pi over 2 for t. So 1 is equal to minus cosine of pi over 2 plus c. Well, cosine of pi over 2 is 0, so this means that the constant c is 1. So if we are given an initial condition, we can actually determine the constant c, and it is equal to 1. This is the unique solution of this initial value problem. So in general, initial value problems under the conditions that we'll see in the existence and uniqueness theorem have unique solutions. So the solution exists and is unique. And this is the case here, so we found a unique solution, minus cosine t plus 1. So on the previous page, c could be anything. Here, c has a specific value, namely 1. And here is a slightly more complicated example. So here is a second order equation that we can also solve by repeated integrations like this. So the example here says that the second derivative of the function x with respect to t is equal to t. So we're going to solve this in 2 steps using 2 integrations. So actually, we're reducing this to a couple of first order equations. So instead of solving the equation for x, let's denote its derivative by y. So y is equal to x prime. It's equal to dx over dt. So the second derivative is equal to the derivative of the derivative. So this means that the derivative of y is, so this is the derivative of x, so it's equal to t. So then we know how to solve this. We saw it in the previous example. We integrate both sides. So y is equal to the integral to the antiderivative of t. So the antiderivative of t is equal to t squared over 2 plus a constant. Okay, but y was the derivative of x, and x is the function that we want to find out. So then we use this answer that we already found for y. So the derivative of the function x is y, which we found to be t squared over 2 plus a constant, c1. So then we do the same thing again. So the function x is the antiderivative of t squared over 2 plus the constant. So then it's equal to t cubed over 6 plus, and then the antiderivative of the constant c1 is c1 times t, and then plus another constant. So the antiderivative is only unique up to a constant. So now our solution contains 2 constants, c1 and c2. So the general solution now is t cubed over 6 plus c1t plus c2. And this is the general solution of the equation. So notice that for a second order equation, we had to do 2 integrations, and we ended up with 2 constants. So in general, this is the case if you have an equation of order n. So if the equation involves a derivative of order n, then you have to do n integrations, and you end up with n constants in the general solution of the equation, if you are not given initial conditions. So this is an example of solving this equation together with conditions. So again, in order to solve the second order equation, so because you have 2 derivatives here, then we need 2 initial conditions. In general, we need as many initial conditions as the order of the equation, as we'll see. So here is how we solve this equation. We take the general formula, the general solution of the equation that we found on the previous page, and we plug in these initial conditions. So the general solution was t cubed over 6 plus c1t plus c2. And the initial conditions here are that when t is equal to 0, then x is 1. So 1 is equal to 0 cubed over 6 plus c1 times 0 plus c2. So this gives us that c2 is equal to 1. And the other initial condition is that x prime of 0 is equal to 2. So we need to look at this function and find out what its derivative is, because the condition is in terms of x prime. So the derivative of this is, the derivative of t cubed over 6 is t squared over 2. The derivative of c1t is c1. And the derivative of c2 is 0, because c2 is a constant. So the derivative is just t squared over 2 plus c1. And then when t is equal to 0, x prime of 0 is 2. So this means that 2 is equal to 0 squared over 2 plus c1. So actually c1 is equal to 2. So this is the particular solution that corresponds to these initial conditions. So it's t cubed over 6 plus 2t plus 1. So again, when you have this sort of initial value problem that has the appropriate number of initial conditions, then the solution always exists and is unique. And this is it for today. Thank you for your attention. So we're going to continue with more first order equations, but in the first homework, there will be a couple of examples like this. So this is what solving ordinary differential equations is like, except that in general, in order to get to the point where you can use these integrations, you have to do some more complicated algebraic manipulations first. So these are just particularly straightforward because you just have to do the integrations. You don't need to first do the algebraic manipulations that you'll see are necessary for most ordinary differential equations. Thanks for your attention.